Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. I'm a Nigerian-born computer scientist who came of age in the USA of the 1970s and 80s. In the 1980s, the most compelling mathematical puzzles and questions that faced high-performance computer scientists were these. What's the speed limit in computing? Or what's the best way to build the world's fastest computer? Can the world's fastest computer ever fit in a room? Can the most difficult problems in mathematics be solved across an ensemble of 1 billion processors that outline an internet? How do we invent a never-before-seen computer? Can a billion processors work together to emulate a supercomputer? It's easier to ask these questions than to provide their answers. But the world worships any inventor who can answer the most difficult questions at the crossroad where new computational mathematics, new computational physics, and the world's fastest computing intersect. A school essay question is this: what is the contribution of Philip Emeagwali to the development of the computer? I discovered the world's fastest computing across the world's slowest processors and discovered how to use the fastest computers to solve the most difficult problems in mathematics. I made those discoveries on the 4th of July 1989. My new computer science opened the door to the world's fastest computer that now occupies the footprint of a football field. The fastest computer is powered by millions of processors. Before my supercomputing discovery, the idea of the fastest computing across the slowest processors was merely a theory or an idea that's not positively true. My contribution to the development of the world's fastest computers is this: I discovered that a billion self-contained processors that were locked together can be programmed to emulate one seamless, coherent machinery that's a supercomputer in reality. My discovery is the origin of the first supercomputer. Becoming a famous computer scientist doesn't happen the way you see them in the movies. I began supercomputing on June 20, 1974 in Corvallis, Oregon, USA. Back in 1974, I was not hailed as a supercomputer genius. The reason was that the world waited for 15 years for me to provide the hard evidence that the world's slowest processors can power the world's fastest computer. At 8:15 in the morning on July 4, 1989, I discovered that using a billion processors to power a supercomputer is useful and doable. School essays on the contributions of Philip Emeagwali to computer science highlight the invention of how to harness the slowest processors to perform the fastest computing. That invention is central to the first supercomputer as it's known today and as it's expected to be known tomorrow. The reason my invention made the news headlines in 1989 was because it heralded the end of the era of vector supercomputers that was powered by only one isolated vector processing unit. Inventing the world's fastest computer demands programming millions of processors, not interacting with thousands of people. As a black supercomputer inventor in the United States of the 1970s and 80s, I discovered the world's fastest computing and did so alone, as well as independently of any institution. In the 1970s and 80s, I was a black inventor that was trapped within all white spaces. In the 1970s and in the USA, the most brilliant sub-Saharan African scientists were not allowed to teach, research, and even present their inventions to the public and compete on the same terms as white scientists. I was the first person to perform the world's fastest computing and do so via parallel processing. Because I was black, I was not allowed to teach, research, and even present my world's fastest computing to the public. In a perverse twist, as computers become faster, the more reliant on parallel computing they become. And parallel computing became synonymous with computer science. Parallel computing is ubiquitous at the frontier of knowledge of the most difficult problems that arise in science, engineering, and medicine. In the early 1980s, my world's fastest computing was rejected when I first presented the technology to universities in the USA. In the mid-1980s, my theorized fastest computing across a new global network of 65,536 processors was rejected in Ann Arbor, Michigan. It was rejected because a black inventor invented it. In 1989, and after I won the highest award in supercomputing, I received invitations to give lectures on the world's fastest computer, and to give those lectures at a time I was the only person in the world that could deliver such lectures. It should not come as a surprise that on YouTube I delivered the most lectures on contributions to mathematics, physics, and computer science. What surprised me in 1989 was that I was often disinvited from giving lectures on the world's fastest computing, even though I was the first supercomputer scientist that came to mind when thinking about how to solve the most difficult problems in mathematics and solve them on the fastest computer that's powered by millions of processors. The disparate treatment was this: a white computer scientist who could only teach the old sequential computing paradigm was hired over the black supercomputer scientist who discovered the new paradigm of supercomputing across a billion processors. Because of the institutionalized racial discrimination in the USA, I became well known, but not known well. Racism is a dangerous cancer of the mind. Not allowing the black mathematician to solve the most difficult problems in mathematics slows down human progress, and does so by excluding geniuses from contributing to knowledge. The irony was that those white supremacists who disinvited me from giving research lectures on my contributions to developing the fastest computers now complained that they couldn't understand the complicated mathematics and the advanced computer science that were behind the invention that I made in the 1970s and 80s. I described my inventions across the 1,000 closed caption videos that I posted on my YouTube channel named Emeagwali. I've been supercomputing since June 20, 1974 in Corvallis, Oregon, USA. After half a century of supercomputing, a huge knowledge gap developed between those that rejected my computer science, my new computer science, and myself. That knowledge gap manifested itself in their inability to replicate my world's fastest computer speeds of July 4, 1989 in Los Alamos, New Mexico, USA. That knowledge gap is visible after watching the 1,000 closed caption videos of my lectures which I shared on YouTube, and then comparing them to the videotape lectures of the leading minds in mathematics, physics, and computer science. The misperception of some white supremacists that Albert Einstein, who is considered the father of modern physics, knows more about computational physics than I do, differed from the reality that I was the only single person to ever record the world's fastest computation. On YouTube, I said much in 1,000 videos about the first supercomputer as it's known today, and I did so because I was the first inventor to understand that the new computer science becomes the world's fastest if and only if it's powered by up to 1 billion processors. I discovered the breakthrough that changed the way we look at computers. In the old way of solving the most difficult problems in mathematics, the fastest computation was achieved by solving one initial boundary value problem of physics. Such mathematical problems arise in multi-scale modeling of biological systems, as well as the large-scale computational fluid dynamics model that must be used to foresee how the coronavirus disease spreads across the densely packed Onitsha market, where social distancing is not enforced. In the old mathematics textbooks, only one such problem was solved at a time and within one processor. In 1989, I was in the news because I discovered a new billion processor paradigm that was a faster way of solving the most difficult problems in mathematics. My new mathematics yields the first world's fastest computing across the world's slowest processors. In my new supercomputing paradigm, I changed the way I looked at the world's fastest computer. I discovered how to perform the world's fastest computations and solve the most compute-intensive mathematical problems in computational physics. And I invented how to solve them across an ensemble of 1 billion coupled processors that shared nothing, and solve them millions of times faster than in the conventional paradigm of solving one problem at a time. I achieved that mathematical breakthrough of solving 65,536 initial boundary value problems, each governed by a system of partial differential equations, and solving them at once and across as many processors that were evenly distributed across a globe. The initial boundary value problem that's governed by a system of partial differential equations is the most useful subject in mathematics. But to be useful, these grand challenge problems must be solved across an ensemble of up to 1 billion processors. I was the first person to discover how to solve partial differential equations and do so across up to 1 billion processors and solve them at the fastest computing speeds. That paradigm shift in high-performance computing, or change in the way we look at the world's fastest computer, went against the prevailing dogma. Prior to my supercomputer discovery that occurred on July 4, 1989, computer scientists believed that it will be fastest to solve only one compute-intensive problem at a time instead of solving up to 1 billion problems at once. That supercomputing dogma of solving one problem at a time and solving it on one powerful processor was encoded in Amdahl's law. Physics is the king of sciences, and mathematics is the queen of sciences. Computer science is not a science in and of itself. Computer science is a science of sciences. The invention of the world's fastest computing that works differently from regular computers creates new sciences. In science, it was not enough for me to say that 1 billion processors could be used to solve the most difficult problems in mathematics. I had to provide the hard evidence that my theory was true. On July 4, 1989, I experimentally proved my discovery to be true. Furthermore, I provided the complete explanations of how I made my supercomputing discovery. I did so across the 1,000 videos that I posted in my YouTube channel named Emeagwali. Amdahl's law was to the supercomputer what Moore's law is to the computer, and what the second law of motion is to physics. Amdahl's law decreed that a speed increase of a factor of 8 would be impossible to attain across 8 or more processors. I was in the news because I discovered that supercomputer textbooks that quoted Amdahl's law were wrong. I proved computer science textbooks wrong when I discovered how to use my new global network of the slowest 65,536 processors in the world to execute the fastest computer calculations and solve the most difficult problems that arise in mathematics, science, and medicine. The poster girl of difficult problems in mathematics was extreme-scale computational fluid dynamics, such as high-stake petroleum reservoir simulations that must be used to nail down the exact locations of crude oil and natural gas that are buried up to 7.7 miles or 12.4 kilometers deep and buried across an oil-producing field that's the size of a town. I used my 65,536 processors to perform the arithmetic operations from the system of equations of computational linear algebra, from my finite difference discretizations of a system of partial differential equations beyond the frontier of calculus. I invented 9 partial differential equations called the Philip-Emeagwali equations. And I invented them by encoding the second law of motion, described in physics textbooks, into them. The Philip Emeagwali equations govern the motions of crude oil and natural gas that flow across a highly anisotropic and heterogeneous producing oil field that's up to twice the size of the state of Anambra, Nigeria. Amdahl's law claims that an ensemble of 1 billion processors couldn't be harnessed and used to solve initial boundary value problems of computational fluid dynamics and solve them with the hoped for speed increase of a factor of 1 billion. I discovered that Amdahl's law was a false theory and an enormous lie that was spread around via computer science textbooks. By its definition, a theory is not positively true. In the 1980s, I was the only full-time programmer of the most massively parallel supercomputer ever built. I discovered how to compute at the fastest speeds and compute while solving the toughest mathematical problems and compute across a new internet. I visualized my new internet as a new global network of 65,536 off-the-shelf processors and standard parts. Those processors were identical, coupled, and equal distances apart. So I was the first person to understand the new supercomputing as fastest computing across 1 million processors. I'm not a science teacher of known facts in textbooks. The 1,000 closed caption videos that I shared on YouTube were my first-person accounts from the unexplored territories of knowledge. My lectures were stories about new partial differential equations called the 9 Philip Emeagwali equations, beyond the frontier of calculus. Until I discovered them, those equations had not been written in any calculus textbook. My invention was how the world's fastest computer can be built from the world's slowest processors. My discovery, which occurred on July 4, 1989, made the news headlines because it was new knowledge that changed the way mathematicians solve their most difficult problems. Until my discovery, the fastest computer speed had not been recorded by a one-person team or recorded across the slowest processors in the world. So my lectures across the 1,000 podcasts and closed caption videos, which I posted on YouTube, were first-person stories from the frontiers of supercomputing. My lectures were first drafts of the history of supercomputing and computational mathematics. I understood that new supercomputer as a radical shift that will change the way we look at the modern computer. That was the reason my discovery of fastest computing made the news headlines. That headline was that a lone African supercomputer genius in the USA had won the highest award in supercomputing and won it for discovering how to harness the 64 binary thousand slowest processors in the world and for discovering how to use those processors to solve the most difficult problems arising in mathematics and physics and solve them at the fastest speeds in computing. Because I was the first person to make that supercomputing discovery, my name, Philip Emeagwali, comes up first in YouTube and for search terms like contributions to mathematics, physics, and computer science. My contributions to mathematics were these. I invented the system of 9 Philip Emeagwali equations, each a partial differential equation. My system of equations is a new mathematical tool used to pinpoint the locations of crude oil, injected water, and natural gas that flow up to 7.7 miles underneath the earth and I invented how to solve the corresponding initial boundary value problem and solve it across up to 1 billion processors that outline and define an internet. My new mathematical knowledge expanded the ever-growing body of knowledge that's known as calculus. It's an absurd oversimplification to claim that calculus was co-invented 330 years ago by Isaac Newton and Gottfried Wilhelm von Leibniz. This claim is erroneously repeated in calculus textbooks and by its teachers. Newton and Leibniz contributed to calculus, but did not invent the subject. The development of calculus is the product of centuries-long evolution. Recent contributions to calculus include the 9 partial differential equations that I invented and my discovery that initial boundary value problems governed by a system of partial differential equations can be solved across an internet that's a global network of up to 1 billion processors. My contribution to mathematics was in the top mathematics publications in the world, including being mentioned in the July 1990 issue of the Notices of the American Mathematical Society. In 1989, I discovered how to solve the most difficult problems in mathematics and physics. I made my discovery on a new supercomputer that's powered by a global network of up to 1 billion processors. My processors outline and define my new internet. That new knowledge that I contributed to modern science and technology include 9 partial differential equations. The Philip Emeagwali equations were my contributions to the existing body of mathematical knowledge. I was a research physicist who came of age in the 1970s and 80s and first won acclaim in 1989. I discovered how to use the laws of physics to gain a deeper and surer mathematical understanding of how to model multi-phase flows of crude oil, injected water, and natural gas that were flowing up to 7.7 miles deep and inside a production oil field that's the size of a town. Furthermore, I was an inventor who invented a new supercomputer that's a new internet. Not only that, I forced those 3 identities to merge within me and find a common but never before seen technology. I visualize my invention as a high-performance communicating and computing machinery and as a new supercomputer that's not a new computer by and itself, but that's a new internet by definition. I was treated differently after my discovery of the first supercomputing across the world's slowest processors. My invention occurred in Los Alamos, New Mexico, USA, and it occurred on the 4th of July, 1989. After the news headlines that followed that invention, the stories chased me rather than me chasing the stories. And the hummingbirds flew towards me rather than me running towards the hummingbirds. I began supercomputing on June 20, 1974 in Corvallis, Oregon, USA. In 1974, few blacks were allowed entry into supercomputer learning and research centers. 12 years earlier, a black student, James Meredith, fought to integrate the University of Mississippi. Without access to education, the likes of James Meredith cannot become supercomputer scientists. That was why I never met a black supercomputer scientist during the 1970s and 80s. And that was why everyone was shocked when a black person won the highest award that computer scientists describe as the Nobel Prize of Supercomputing. I won that prize alone back in 1989. My discovery of the world's fastest computing was a record-breaking and sustained performance. It was recorded in the June 20, 1990 issue of the Wall Street Journal. I was in the news on the day Nelson Mandela was released from prison, but I was boycotted in the manner South Africa was boycotted for apartheid. That boycott was significant because in schools, the bearer of new knowledge or scientific discoveries transmits it through the spoken word. A scholar without lectures on YouTube is like radio without sound or a movie without images. Those early boycotts of my lectures of the 1980s were the scientific equivalent of mainstream radio stations working together to keep black music off the air. In the field of supercomputing of the 1980s, most of the 25,000 paid positions were reserved for white males. I gave hiring lectures for some of those paid positions. After each hiring lecture, the supercomputing position was closed. When it comes to racial diversity in American academia, the fields of mathematics, physics, and computer science are half a century behind society. The racial diversity in the supercomputing world of the 1970s and 80s, the 2 decades during which I came of age, was like the racial diversity in US mainstream radio broadcasting of the 1920s and 30s. In the 1940s and 50s, African American entertainers were forced to use a different door to enter white radio stations. In the 1970s and 80s, my access to supercomputers were withdrawn after it was discovered that I was black and sub-Saharan African. A school essay question is this: who is the father of supercomputing? Asking who is the father of supercomputing is like asking who is the father of rock and roll. No one person started rock and roll. Notwithstanding, if 2 persons can claim the title of the father of rock and roll, there will be Little Richard and Chuck Berry. Elvis Presley will not be included because he didn't write his songs. Elvis Presley brought rock and roll to a larger audience and became the face of white rock and roll. Unlike Elvis Presley, the songs of Little Richard weren't played on mainstream radio stations. Instead, the covers of Little Richard's songs that were recorded by Pat Boone and the Beatles were played on white radio stations. And those covers became hit songs. Fast forward 3 decades from the 1950s, I discovered that white scientific communities weren't ready to hear my new presentations on fastest computing, just as mainstream radio stations didn't play black music. And white research scientists were paid millions of dollars to falsely claim the credit for inventing the Philip Emeagwali computer, which I invented half a century ago. When I began supercomputing on June 20, 1974 in Corvallis, Oregon, USA, dividing the most compute-intensive problems from large-scale geophysical fluid dynamics and dividing such difficult problems into a billion lesser challenging problems, and then solving them across smaller problems. Across an ensemble of 1 billion processors was science fiction. For those reasons, large-scale computational physicists and mathematicians were frightened and fled from computing across processors. The June 14, 1976 issue of the Computer World magazine summed the difficulty up in an article that was titled, quote, "Research in Parallel Processing, questioned as a waste of time," unquote. Vector supercomputer scientists fled from parallel computing because they believed it would be simply impossible to harness thousands of processors and use them to solve the most difficult problems at the frontiers of knowledge, where new mathematics, new physics, and new computer science intersect. I was castigated, ostracized, and banished during my 15-year-long quest for the world's fastest computer. That quote-unquote new computer wasn't a computer in and of itself. It was a new internet in reality. I discovered my new internet, a new supercomputer, within the bowels of an ensemble of the 65,536 slowest processors in the world. At its core, I defined my world's fastest computing as occurring when 1 billion processors work together as one coherent unit that can be used to solve as many problems at once. Such less challenging problems arise from dividing up the most difficult problem in mathematics into 1 billion less difficult problems that are mapped with a one problem to one processor correspondence. Each processor operated its operating system and had its dedicated memory. In contrast, and in symmetric multiprocessing, several processors share a single memory and share the same operating system. As a supercomputer scientist, I came of age in scalar supercomputing of mid-1974 in Corvallis, Oregon, USA, and in the first supercomputing across the world's slowest computers that I discovered on July 4, 1989 in Los Alamos, New Mexico, USA. In the 1970s, parallel computing was mocked, ridiculed, and dismissed as a tremendous waste of everybody's time. It was then believed that 1 billion processors could only yield a maximum speed increase of a factor of 2, and do so if and only if 50% of the compute-intensive problem can be solved at once. That parallel process speed increase becomes a factor of 4, 10, and 20, and becomes so when 75%, 90%, and 95% respectively of the large-scale computational fluid dynamics code could be solved at once. I was in the news in 1989 because I was the computational mathematician who discovered how to unlock Moore's law for one processor and discovered how to mathematically solve 1 billion problems at once and solve them across an ensemble of 1 billion processors. A question in school essays is this: what is the contribution of Philip Emeagwali to mathematics? The first world's fastest computing across up to 1 billion processors that work together to solve the most compute-intensive, the most difficult problems is my contribution to mathematics. My new knowledge must be used to address the biggest challenges that are governed by partial differential equations, Such equations occur at the frontiers of calculus, algebra, and physics. For example, a system of coupled nonlinear partial differential equations must be solved to deeply understand the spread of the coronavirus across the crowded Onitsha market of my country of birth, Nigeria. That's my contribution to large-scale computational mathematics. The modern calculus will not be useful without the supercomputer or without solving the most compute-intensive problems in calculus and solving them across an ensemble of millions of processors. The technique of parallel computing was to a large extent invented by computational mathematicians for computational physicists. After my discovery that the world's fastest computers can be built from standard parts called processors, parallel supercomputing made the vector supercomputer obsolete and reduced it to the technological equivalent of the horse and carriage that was replaced by the now obsolete steam engine. I discovered the fastest computing from the slowest processing. The obstacle that I overcame before I could discover the first world's fastest computing across the world's slowest processors was to become the first person to figure out how to use the slowest processors in the world and use them to solve the most compute-intensive problems in the world. Those were the most difficult mathematical problems that must be solved across the millions of processors that outline and define the extremely fast supercomputer, and solve them at the fastest possible speeds in the world. In the supercomputer textbooks of the 1980s, that obstacle was described as overcoming the bottleneck called Amdahl's law. In prose, Amdahl's law decreed that when capital P, number of processors, is used to solve a compute-intensive initial boundary value problem of calculus, such as those in large-scale computational fluid dynamics, and if the serial fraction of that grand challenge problem is lowercase f, then the expected increase in supercomputer speed will be 1 divided by the sum of lowercase f plus 1 minus lowercase f divided by capital P. The expected increase in parallel process speed across 1 billion processors will only be as large as the weakest link will permit. Computer scientists often ask, how did I uniquely name my 65,536 processors that I harnessed to execute the world's fastest computing of 1989? Because I invented new supercomputing, I had to come up with a new name for it, and do so for the same reason a newborn infant must have a new name. At various times in the 1980s, I named it a hyperbole supercomputer. Then I shortened that name to a hypercomputer, and it was finally renamed the quote-unquote Philip Emeagwali supercomputer. The Emeagwali computer is a new global network of millions of processors, or a small and physically realizable copy of the internet. That's not a science fiction. Such idealized internets might not be visible around a globe, but will be intelligible to the supercomputer scientists. If necessity is the mother of invention, I say the most compute-intensive problems in science, engineering, and medicine necessitated the pushing of the frontiers of the fastest computers. The supercomputer was invented out of necessity and invented by mathematicians for mathematicians. The partial differential equation of the mathematical physicist is the most recurring decimal in fastest computing. The quest to use an electronic machinery to solve the ordinary differential equation of calculus that governs the trajectories of missiles was the difficult problem that motivated the invention of the first programmable computer. That computer was created in 1946 and at the Aberdeen Proving Ground that was 26 miles outside Maryland, Baltimore, Maryland, the birthplace of my wife, Dale. That all-vacuum tube supercomputer of 1946 used 18,000 vacuum tubes. My quest was for the fastest computer that could be used to solve the most difficult problems in mathematics and physics. An example of such grand challenge problems include the initial boundary value problem of calculus that's governed by a system of coupled nonlinear and time-dependent partial differential equations that's always at the mathematical physics core of any computational fluid dynamics code. In particular, and for everyday uses, a system of partial differential equations is at the calculus, algebra, and physics core of the general circulation model that governs the motions of water and air that enshroud the earth. Such partial differential equations interest astrophysicists because they also govern the motions of the fluids that circulate around distant planets and stars. I invented Philip Emeagwali computer to be used to solve the most compute-intensive problems that arise as extreme-scale computational fluid dynamics modeling. A poster child of such grand challenge problems is the general circulation model within the Earth's concentric atmosphere that's represented by the domain of the arising initial boundary value problem. Another poster child of computational fluid dynamics is the supercomputer modeling of the limited air circulation of contagious viruses, in particular the simulation of a once-in-a-century global pandemic and how it spreads inside the 2,400 train sets of Spain's Madrid metro system. Each train packed passengers like sardines. The reason I talked about distant planets, stars, and galaxies was that I was trained as an astronomer in the mid-1970s in Corvallis, Oregon, USA. I received my earliest job offers as an astronomer rather than as a computer scientist or mathematician or physicist. The reason was that the US Office of Personnel Management rated me higher as an astronomer. In 1989, I was in the news because I discovered the fastest execution of astrophysical and geophysical fluid dynamics codes. The movements of the 8 planets around our sun obeys the laws of motion of physics. The ebb and flow of the tides of the water and air that enshroud the earth obeys the second law of motion, described in physics textbooks. That second law of motion was discovered 330 years ago. The second law of motion was discovered in prose, but it was coded in algebra as force equals mass times acceleration, or F equals ma. My contributions to calculus were these. I reformulated the iconic formula F equals ma into a system of 9 coupled nonlinear and time-dependent partial differential equations that governs subsurface motions of multi-phase flows across a porous medium, such as the 65,000 oil fields around the world that include the supergiant oil fields in Venezuela, Kazakhstan, and Russia. My new system of 9 equations governs the flow of crude oil, injected water, and natural gas flowing across an oil-producing field that's up to 7.7 miles or 12.4 kilometers deep and often the size of Onitsha, Nigeria. My contributions to algebra were these. I discretized those partial differential equations beyond the frontier of calculus into partial difference equations beyond the frontier of large-scale algebra. Furthermore, I reduced my algebraic formulation to computer codes. In 1989, I was in the news because I recorded the world's fastest computing. I did so by executing my 65,536 supercomputer codes at once and across and with a one-to-one correspondence with my ensemble of 65,536 processors. At its physics core, calculus is about changes and motions that range from the geophysical motions of the Earth's liquid outer core, that's very hot, very dense, to the astrophysical motions of distant stars. My quest was to theorize my governing system of coupled, nonlinear, and time-dependent partial differential equations that encoded the fundamental laws of physics of fluid dynamics. I visualized my computational fluid dynamics codes not as executing within one processor, but as executing across my ensemble of 65,536 processors. I theorize each processor as parallel to each of my 65,536 divided atmospheres, or as many blocks of oil fields. Those individual atmospheres completely and tightly enshrouded my geometric metaphor for the entire Earth's atmosphere. My geometric model was a concentric sphere that was 62 miles thick. That model had an inner diameter of 7,918 miles. My quest was to discover how I could harness and use my 65,536 equidistant processors to solve the most difficult problems in mathematics and physics. Towards that end, I visualized my processors as braided together around a globe and used to solve 64 binary thousand equally compute-intensive problems, and used to solve them with a one processor to one problem mapping and correspondence that preserved nearest neighbor proximities, which in turn was the mathematical precondition to my recording the world's fastest computing. In the early 1980s, my grand challenge was to invent the techniques and technologies to be used to solve initial boundary value problems and solve them with up to 1 billion processors and with a speed increase of 1 billion. My contribution to the mathematical solution of such compute-intensive physics problem was the cover story of the flagship publications of top mathematics societies, including the May 1990 issue of the Siam News that is published by the Society for Industrial and Applied Mathematics. My record-breaking sustained performance in computing was mentioned in the June 20, 1990 issue of the Wall Street Journal. My contribution to mathematics was that I turned that mathematical fiction of the fastest computing across the slowest processors into a non-fiction. That world's fastest computing is the new knowledge that I discovered that was used to upgrade the parallel computer to the stature of a supercomputer. The world's fastest computer of today became a non-fiction after my discovery that occurred at 15 minutes after 8 o'clock in the morning of July 4, 1989 in Los Alamos, New Mexico, USA. Thank you. I'm Philip Emeagwali. Thank you. Thank you very much.
Insightful and brilliant lecture.